So, yeah. If we think about the process of doing exponents, once again, which we talked about last time, the logarithm is the inverse of the exponent function. So if I have y is equal to 4 to the x power, then I would have x negative 1, 0, positive 1. Y would be 1, 4, 1, and 4. Notice it is okay for us to have negative numbers as exponents, but we should not get negative numbers as the result of the exponent. Then how would I write the inverse function?
Flip it.
So what would that look like?
It's going to be x is going to become 1 over 4, then y is going to become negative 1, so on and so on.
Okay, so I flip these things around. X would be 1/4, y would be negative 1. X would be 1, y would be 0. X would be 4, and y would be 1. Okay. I'll just throw another one in here. If x is 2, y would be 16. And here, if x is 16, y would be 2. But how do I write the actual function? How do I write the inverse function of an exponential function?
Use x and y.
Actually, no. I just want to write the final
Function,
form.
function negative 1 of x.
No. I want to say y equals what?
The logarithm base x of 4.
Yeah.
No.
4 of x.
Logarithm base 4 of x.
Of 1 equals. So
Logarithm base 4 of x is equal to y. So if I put in
1.
the logarithm base 4 of 1/4, that's negative 1. If I say the logarithm base 4 of 1 is 0. The logarithm base 4 of 4 is 1. The logarithm base 6 or base 4 of 16 is 2. Okay, so that's how I write it. Notice when I put numbers into the logarithm, they have to be positive numbers. When I put the numbers into the logarithm, they are positive numbers. The ones that come out of the logarithm can be negative.
Henry?
All right. Notice the numbers that are here after the word logarithm are all positive numbers. Notice that when I take the logarithm, I can get a negative result. I don't always get a negative result, but it's possible. If this is a fraction, like 1/4, the number I get will be negative. Now I'm going to graph this. If x is 1/4, y is negative 1. If x is 1, y is 0. If x is 1, 2, 3, 4, y is 1. If going out here to 16, it would be the 1, 2. Notice then, if you understand the graph, you can look at the graph, then you'll be able to say the domain is limited to only the positive numbers. The range is not limited. I can have any range number I want to, but my domain is limited just to positive numbers. You'll also notice that right here, the logarithm of 1 is 0. If I go smaller than 1, these are all negative logarithms. Greater than 1, these are all positive logarithms. Illustrated by the examples. Okay? So, this is review of the logarithm relationship. Okay? But now, we don't want to use 4 as a base. We want to use the number e as a base for our logarithms. Because just like in science, we want to have the exponential function with e as a base. In science, we also want the logarithm function to have e as a base. So, this is what happens sometimes. It is a small letter L and a small letter N of x. This is called the natural logarithm. That means the same thing as log base e of x. But we don't want to keep writing that over and over if we're just going to use that all the time. So then scientists use ln of x. Now, notice this is a small letter L. If I print it, or write it with printing instead of cursive, it looks like this.
I thought it was in, actually.
But it's not.
Looks like a 1N.
Is it a 1? No. Is it an I? No. It's a small letter L. How do you tell? You can't. Right? So then when I write it on the board, I use this. I use the cursive so that you can tell it's a small letter L, because that's what it actually is. Now, depending on the teacher or whatever else, they might not do that. I find it helpful to put that in there so that I know what I'm talking about.
Yeah.
When you see it in a book, the letter L is not exactly the same as the number 1 in typesetting sometimes. Way back in the day, typewriters didn't necessarily, well, this is how I remember it. In order to hit the 1, you would have to go up in the far corner, and it's easier just to type an L. So back in the day when they were using typewriters, they would just use the small L instead of 1 because they look the same. But we're going to have to do this when we write it so that we can keep track of it as being the natural log. That's what this means, natural log. Why is it called natural? Because it appears in nature. It appears when you have bacteria or things that are growing continuously, then it's natural. So they call it the natural logarithm. Now, this, however, is a problem when you start working with computers. Because with computers, they don't always use this. Sometimes they just call it log, and they mean the natural logarithm. That's confusing, isn't it? So we'll try not to do that. But there are computer systems out there that when you type log of whatever it is, it's actually taking the natural logarithm. So you have to be aware of that. It's possible. On your calculator, however, when you have log on the calculator with an x here, this logarithm is actually defined 3 lines means defined. It's defined to be the logarithm base 10 of it. So on your calculator, if you do logarithm of 100 and you don't have the e in here and you don't have ln and you don't have anything else, I want you to find out what your calculator tells you. That means you have to have your calculator out and you need to push the buttons on the calculator.
2.
2. What is that actually telling me?
Says it's 26. Yeah.
10 to the second power is equal to 100. That's correct. Now, what if we take the natural logarithm of 2.718? What is that approximately?
1.
1. What does that mean?
So weird, Mike gave me 0.9.
Yeah.
He
Well,
said
this
approximately.
right here, approximately. Yeah, it's approximately.
Well, that's,
Yeah, that's the right answer. Thank you, Jeffrey. That's the right answer. Okay, so then what does that tell me? What does this mean in exponent?
that one I know.
Each of the first two is 2.718.
E to the first power is approximately 2.718, which is true. Okay. So if you get confused, you can try this, all right? If I put in a 10 or 100 and the logarithm gives me 2, then I know it's a common one. If I put in this value and I take the logarithm and it gives me a 1, then I know it's a natural. All right, so
So does it matter which one you write, E or ln, like, because they're the same, that means.
okay, logarithm base E is the same as this symbol, ln. If I ask you the question, does it matter which one you write? Well, kind of it does, because in certain situations, everybody's writing it this way. And if everybody's writing it that way, you should not write it that way. Depends on what kind of people you're hanging out with.
So I have to get.
Not all people are bad,
No, you're absolutely right. Not all people are bad.
but not all people are good.
That's correct. You gotta be careful. You can't just hang out with anybody you want to, or anybody that's convenient. You have to judge them
So
as
you're
to their
saying
suitability for their
I can't
hanging
hang out with the killer?
Well, you sure could if you're trying to help them and rehabilitate them, right? You could go over to the jail and say, I need help. I'm here to bring some joy into your
You're being
life.
serious, oh.
Okay, well, sure.
So what does this 3 line stand for?
It means defined. It is by
Okay, it's not
definition.
equal.
It's equal by definition. All right, so then, if you want to find e to the first power, you also have a button on your calculator that does e to the power. So you could go e to the first power, and that would give you e. And then if you take the natural logarithm, it would be 1.
2.718?
Yeah,
28182.
that's right. Now, what's the natural logarithm of 1?
0?
0, because e to the 0 power gives you 1. Always. The logarithm of anything is the logarithm of 1 with any base would be equal to 0. Okay. So, if we have a situation where we want to find a particular number, we can think about how it should be written in exponent form. If I have something that looks like this, natural logarithm of a is equal to 0.33. Well, I'm going to rewrite that now in exponent form. What would that look like?
E to the A power, no, E to the 0.33 power is A.
That's correct. Because they are inverse functions, right? If I put a into the logarithm, I get 0.33. So if I put 0.33 into the exponent, I get what a is. So let's see if I have my calculator able to do things here.
1.39.
Well, my calculator again doesn't actually do this. So if I have maximized it. Okay. So e to the x of 0.33, right? 1.39. Okay. So you don't have to, in a sense, go through a long process of mathematics to go from this to this. It's just the inverse function. So if you can just rewrite it and then you can do this on your calculator. It's not a problem. All right, so that's fine. So then, the next thing that happens is that we start to do things as far as mathematical operations with logarithms. And one way to understand this is to say a logarithm is an exponent. So if I look at that and I say, where is this 0.33? This is the exponent that goes on there. If I say log base 4 of 1/4 is -1, this is the exponent. The logarithm is the exponent that goes on 4. So then, properties of logarithms are also properties of exponents. And I have to apologize. This is not easy, and it's easy to get confused. But we'll try to keep this going. So we have what are called basic properties. These are what we've already talked about. The logarithm base A of 1 is equal to 0. It doesn't matter what base it is. The logarithm base A of A. What exponent do I put on A in order to get A?
1.
1. So the logarithm base A of A is 1. That always works well, no matter how. What if I have the logarithm base A of A to the K power?
A raised to something. Okay.
This is K.
Oh, because the previous rule for the log of A, or no, the log base A of A makes it 1, so it just leaves K left, right?
No.
What?
Okay, your understanding unfortunately is faulty.
You gotta do your
Okay?
exponent rule.
It's faulty. It's exponent rules, but it's also inverse function rules. The idea of saying log base A of A is 1, so that means that this part is 1. That doesn't work, because 1 to the K would be 1. So it's not. Okay. So we can't separate, we can't take the log base A of A and then take it to the K power. All right. This. And this is true, that the logarithm base A of this number is equal to the number K.
Mr. Flowers,
Yes.
can we try this with numbers? Because
Sure.
I'm
Yeah, that's absolutely a great idea.
Yeah.
Right.
We simple numbers.
All right, sure.
No.
The logarithm base 17 of
Okay.
1 is 1. The logarithm base 11 of 11 is 1. The logarithm base 5 of 5 to the 10th power is 10.
Okay, can you explain that? I mean, you're trying to explain that, sorry.
No, that's fine. What does this mean right here?
That's the power.
This is the power. So if I take 17 to the 0 power, I'm going to get 1. What is this right here? This is the power, it's the exponent. If I take 11 to the first, I get 11.
Correct.
What is this right here?
That's the power.
It's the power, the exponent. So 5 to the 10th power is 5 to the 10th power. Right?
So we didn't need to write the 0 and the 1 over there because it's understood, is what he's saying. But-
No,
but
if
here we have to write it.
when I put this on the test and I say, what is the logarithm base 33 of 1? Question mark.
0.
0.
Oh,
Okay? Or what is the logarithm base 5 of 5 to the 10th power? 10. That's the answer. And when you say the reason why this works is because you could rewrite it as exponents. Yes. But the actual question that we are being asked is, what is the exponent? The exponent, in order to make this work, to get 1, the exponent is 0. So that's why that's the answer. All right, so now we're going to kind of, how shall I say this, go into the alien universe, the alternate dimension.
we are? Are
Yeah.
you taking us to the promised land?
No, no.
Nice taking us to areas you want.
Yeah, this is right. This is where the aliens live.
That thing, everyone is on that now. Oh my
Yeah. What's 100 times 1,000?
100,000?
Yeah. Because
Okay.
you just add the zeros. Well, no.
You choose, you add the zeros. Okay, so now this in exponent form would be what?
10.
10 to the 2nd power. And this is 10
10
to
to
the
the
3rd.
3rd.
And what result do I get?
10 to the 5th.
10 to the 5th power.
Yay.
I added the logarithms, right?
Mhm.
All right, the exponents. And exponents are actually logarithms. Okay? So, what is the log base 10 of 100?
2.
2. What's the logarithm base 10 of 1,000? 3. Okay. So this is how we're going to write it. The logarithm base 10 of A
Okay.
plus the logarithm base 10 of B
Okay.
is equal to the logarithm base 10 of A multiplied by B. Because the logarithm base 10 of 100,000 is 5.
I'm sorry. Dude.
What is this actually saying to us? What this is actually saying
It's
is,
saying to us, okay, we're gonna go by.
yeah, we're now gone. We've made our first leap into the
I'm
alternate
just kidding.
So if I have two things which are being multiplied over here, this is 100 times 1,000. That's 10,000. This is a bigger number. When I do the logarithm of that number, that would be 5. The logarithm of the first number was 2. The logarithm of the second number was 3. If I add the logarithms here, I get the logarithm of the multiplication over here.
That's amazing.
So logarithms take multiplication and they make it into addition.
That's fun.
Yeah. And we talked about this a little bit in terms of your response to stimulus. If you are in a dark room and you're looking around, okay, and then all of a sudden somebody turns on the light, it multiplied the amount of energy tremendously. But to you, it was only a few steps because your eye just adjusted to it. Because instead of multiplying its response, it just moves it up using logarithms. So that makes us able to be sensitive to different things.
Dun, dun, dun.
So this situation then, when I say that when we multiply numbers, then we can add the logarithms. It works either putting things together or breaking things apart. So I could say the logarithm, I could use natural logarithm. Natural logarithm of 6 is equal to the natural logarithm of 2 plus the natural logarithm of 3. Since 2 times 3 is 6, then this is also the case. But pay attention to what is not happening here. We are not eliminating the logarithm. We are just breaking it up in pieces.
So does that only work with E and common logarithms?
No, it works with any logarithm, no matter what it is. So from here on out, when I write log, I usually mean any logarithm. Okay? I'll try to be clear when I don't. So if I say the logarithm of x of y, that's the logarithm of x plus the logarithm of y. I can break things down if I want to, or I can put them together. So in some situations, we want to break them up, and in other situations, we want to put them together. Depends on what we're trying to do. Yeah, we'll get there. We're getting close to what I want to do. So, well, what happens if we divide things?
Probably subtract them.
Sure. So if I have 150 divided by 50, that's equal to 3, right? So then the logarithm of 150 minus the logarithm of 50 is equal to the logarithm of 3.
Why is it minus? I thought you were dividing. Oh, yeah.
Dividing.
Multiply.
Logarithm.
Yep.
So yeah,
Sorry.
we have a division problem, but we can change it into a subtraction problem.
Yeah.
Now, way back in the day, before my time.
Oh, you're saying so it was like, you know, like 50 some years ago?
Yeah, so.
He's like, yeah.
When people had complicated calculations to do, where it involved complicated numbers, they would actually use a table of logarithms. And so then they had these tables that went on for pages and pages. And so you say, oh, I want 7.56 multiplied by 4.22. You want to do that multiply. So what you would do is you would look up the logarithm of this, and then you look up the logarithm of that.
Then you add it.
You would add them together, and then that result, you would look in the table to see what number that came from. And so then it was shorter just doing an addition and then looking up numbers instead of going through and multiplying this whole thing out. And what you would have to do is you would have to get your accuracy would not be that great unless your table went to like 4 decimal places, which would be a lot, right? You're gonna have everything from 0 to 1.999, and you're going to have it by thousands or 10,000s. That would be a huge thing. Well, it was. But they did it. And Apollo 11, right? They went to the moon with that kind of ability. They weren't doing this kind of multiplication.
Oh yeah, that was 50 years ago. So
And I was around.
I had a pineapple moment.
I went outside and I looked up at the moon just to say, yes, I'm looking at the moon and there's somebody above me.
Wait,
There's
at
a literal man on the moon.
At the time or like,
At the time,
oh, at the time it's like, whoa.
July
Yeah,
of
it was not
1969.
It's not true.
Well, still listen to
So-
those. They're
All right.
just jealous because they didn't make it on the moon.
So now we have
Sarah,
another property which is very
Actually, the
common,
Russians are the first
which is very helpful.
did you say Russians?
The Russians.
Did you hear me just?
States.
The Russians.
Sputnik.
Sorry, Sarah was saying something
Yep,
about
and what was his name? Gagarin?
Another
The first astronaut was actually a cosmonaut.
These names are strange. The Russians.
All right.
They're
Now, what happens if I take 10 to the second power and I take that to the third power?
Logarithm is 2.
It'd be 10 to the 6.
It's 10 to the sixth power.
Yes.
Shoot.
Okay? So, if I have the logarithm base 10 of 100, that's equal to 2. The logarithm base 10 of 10 to the 6th is 6, right? So what happened here? I multiplied by 3. My first logarithm was 2, and then I do a thing to it, and I get a 6. So what does that actually look like? This is everybody's favorite logarithm property. And that is logarithm of a to the b power is equal to b multiplied by the logarithm of a. So when I have an exponent on a number inside a logarithm, I should put parentheses on this. When I have this, it's the logarithm of this thing, then this exponent will actually come out in front and be multiplied. It's important that you know that this is multiplying. So if I say, what's the logarithm, base 10, of 100 to the 7th power?
7 times the logarithm of 10.
Logarithm base 10 of 100. That's just 2, so it's 7 times 2 is 14. So whenever I have this exponent possibility, then I'm able to get that out. Well, this is,
So,
go ahead.
100 becoming an exponent now, or is it the result? Because is it over 10, or we can remove the 10, the log 10, and just put 100, there's no problem?
No. If I ask you this question, what is the logarithm base 10
Mhm.
of 100 to the 7th power?
Okay,
You can take the 7 and put it out in front
yeah,
and multiply it by this. And what is the logarithm base 10 of 100? It's 2.
Yeah.
So this is 7 times 2.
okay.
So, let's do this. If I have the logarithm, and we'll just use logarithm base 10 of 2 to the 13th power.
13 times the logarithm base 10 of 2.
So this would be 13 multiplied by the logarithm base 10 of 2. Okay, so I want you to do these both on your calculator. Right? Logarithm base 10 of 2 to the 13th, and 13 times logarithm base 10 of 2.
It's 3.9.
329, yes it is. So both of these are the same, right?
Mhm.
And what's really interesting, of course, is how does your calculator do this? How can this thing with electricity coming from a little battery, how can it actually know what the logarithm of 2 to the 13th power is? And of course, it's really complicated. We're not going to talk about that right now, but it's pretty amazing that we have these machines that can do this. All right. Now there's one other thing I want you to see, and I don't like it. I wish it did not exist, but it
Oh,
does.
please, we're not gonna see the
So-
scary monsters, are we?
Yeah, this is a scary monster. I'm sorry, but I'm telling you ahead of time. I'm just going to drop it. So, A to the power of the logarithm base A of x is equal to x.
Jesus. I can't even think through
Okay.
Yeah.
Now, initially, I can say this doesn't happen very often, but it does happen on occasion. But it does happen. So, what does this actually mean? What if we were to rewrite this in logarithm form instead of writing it in exponent form? Right now it's in exponent form, right?
Yeah.
So then we would say, if I had a to the 4th, the logarithm of a to the 4th is equal to x.
Logarithm base 10a is equal to logarithm of a to the x.
So then I would write 10. This would be if it's base 10, right?
Yeah.
If this is logarithm base 10 of a to the 4th is equal to x. Then what I would say is 10 to the x power is equal to a to the 4th. Because the base is 10, the exponent is the x,
Yeah.
and it gives me a to the 4th, right?
Yep.
So if I'm going to have this, I would write it like this.
True.
Okay? Well then,
He's laughing.
if I say, if I want to make this into that, okay, then I have to take the base, put it down here.
Yeah.
I take this part, put it there.
Then I
and
take the x
goes
out.
there, right?
Yeah.
Okay. So then here, this would be logarithm.
Okay.
I'm now looking at this right here. I'm translating it. So this is logarithm base A.
Is that, wait, before you go, is that logarithm base a from the first to the second a?
This is this one here.
I know, the big A right in the front, is that,
This big
Yeah.
A is the same as that big A.
oh,
Okay. So this is, I took, I'm trying to get my mind around this, which is hard. Okay.
Even
So the 10 became the base of the logarithm. So So now A becomes the base of the log.
Alright,
This thing here
goes on the outside.
was on the right side. So this is logarithm base A of x. And then this thing here is in the logarithm. This thing here is in the logarithm.
Yeah, okay. So, okay. So what happens to the big A?
Okay. This is true. This thing that I wrote, this monster, this is true. Okay? And what we're doing is we are doing the inverse function. Right?
Okay.
So instead of taking the logarithm of an exponential thing, we're doing the exponential of a logarithm thing, which still gets us back to the original.
You added those before you erased them, right?
Hmm?
No, we didn't add.
They were set equal to each other?
They were set equal to each other. There's no adding.
We're multiplying.
He's gonna write it again, don't worry about it.
All right. Yeah. Well, log base A of x is equal to log base A of x. It's true. It's just true. Now, this thing does happen in some situations. For example, if I say, if I say something like, the natural log of b is equal to 0. Well, what I could do here is I could take both of these things and take e to the power. So this would be e to the power of the logarithm of b is equal to e to the power of this. So once again, I see this has a logarithm in it. And I say, okay, what I'm going to do is I'm going to take e to that power. And when I have the base and the logarithm in that setup, they cancel each other out. So this tells me then b is equal to e to the 2. Like I said, I just don't like it. I don't like working with it. But it's something that some teachers say what you're going to do in order to solve this problem is you're going to take the exponent of both sides. I would prefer to rewrite it according to the definition. I think it makes more sense. But anyway, that's what some people do. All right, so these are all different properties of logarithms, things that happen in order for us to be able to combine logarithms together. So what happens is that we have certain formulas that use this kind of thing, and we want to be able to make it happen. So let's say I have the logarithm, we'll just say it's base 10, of x times y squared times the square root of 0. And my instructions are to split this up. Now, the textbook doesn't say split this up. It says write each expression as the sum and or difference of logarithms as a single quantity. Great. Split it up, that's what they mean. Okay.
We're just gonna do it.
Yes, we're just going to do it. How are we going to do it? Well, the first thing we look for are the things that are being multiplied. We're going to make them into addition.
No.
Log of X plus
It's the logarithm of x plus the logarithm of y squared plus the logarithm of square root of z. We still have logarithms. We changed it into addition, but the logarithms don't go away. Logarithms stay logarithms. It's tempting to say, oh, well, you split it up. Well, you split it up, but you have to put logarithms on everything.
Square root of z.
Square root of z, thank you. Well, now what happens?
You can't do anything because there's no
Can.
No, you can't.
Because y to the second power.
Yep.
So that means we can take that 2 and bring it out in front as one.
What? What?
That's
That's crazy.
it is. They used to say crazy like a fox.
I'm good.
Okay, so keep that. All right.
Into the square root.
Yeah,
What about the square root?
can we do a division there?
We do not.
No.
That one I don't know. I can't.
What is the exponent for a square root?
Half.
1/2. So this is the logarithm of z to the 1/2 power. So we're going to say plus 1/2 logarithm of z.
Ooh.
So we can take a thing which has a bunch of logarithm of a lot of combinations, and then we can split it up into different combinations that use logarithms. Multiplying becomes adding, so and the exponents come up front, all that happiness. But we can also go the other way. So
we just leave it like that?
So yeah, because we've split it up
And that's
into,
it?
and as they say it in the instructions, they say the sum and or difference of logarithms of a single quantity. So that what they mean is it's just logarithm of x. It's not x squared or cubed or something. So there's no easy way to explain what we're doing here, but what we are doing is that we're taking all the multiplying and making it addition. We're taking all the dividing, making it subtraction. And all the exponents, we're taking them out in front. That's what we're doing. Well,
Wow.
what if I had something that looked like this? Logarithm of y is equal to, and this is base 10. Logarithm base 10 of y is equal to 2 plus 3 times logarithm base 10 of x. I want to combine this now.
We'll first bring the 3 over and put it as an exponent.
Okay, I can take the 3 and make it into an exponent on here. So I have logarithm base 10 of y is equal to 2 plus logarithm base 10 of x to the third power. Now this is where it gets a little dicey, okay? I want everything to be logarithm of base 10. So 2 is equal to the logarithm base 10 of what number?
Exponent.
100. So this is logarithm base 10 of 100 plus logarithm base 10 of x third is equal to logarithm base 10 of y. What can I do when I'm adding these logarithms?
You can make them multiply.
I can make them be in a multiply. So this is logarithm base 10 of 100 multiplied by x to the power. And then this is where we have the magic. So we had monsters, and now we're having magic. So the magic right here is if they are both logarithm base 10, then those things that come after the logarithm have to be equal to each other. So then I can now just say y is equal to 100 x to the third. Now, which one of these formulas do you think is easier to work with?
I guess it depends on what they want.
In the first one, that's actually a straight line formula because it's y equals mx plus b. 3 is the slope, 2 would be the intercept. Okay. Well, this is a cubic. That's more complicated generally than a straight line, but it has just the x's and the y's instead of the logarithm. So this happens a lot. What will happen is some kind of a chemical reaction will happen, and you look at it and you say, okay, that looks like it could be a logarithm. So then you put the numbers in there and say, okay, if I change the numbers, instead of considering them just regular numbers, if I make them logarithms, then I can get a straight line. So I'll take the logarithm of x and the logarithm of y and see if I get a straight line. And if I do, then I can rewrite it. So you can actually make a formula for a relationship by taking the logarithm of x and the logarithm of y and making that into a straight line relationship. Happens all the time. All right, so let's do a couple of others of this. Oh, well, yeah, I think it, okay. Because earlier I said I wasn't feeling well, right?
I know, what happened to that?
Yeah.
Well, I was doing logarithms. So we're gonna stop.
Oh.
5 minutes early.
All right.
She's happy. Hey Jeffrey,
Yeah.
I still don't get that one problem. Can you just help me start it out, and then I think I can figure it out
Sure.
real quick before you.
And I will post this video in the resources section of Blackboard. And
So